Walk into any modern commercial skyscraper, and you will notice vast open spaces stretching 10 or 12 meters between support columns, all held up by floor plates that look incredibly thin. These floors are made of concrete, a material prized in construction because it handles compression well. If you squeeze concrete, it holds firm. But if you pull it apart, putting it in tension, it cracks. This animated cross-section shows the mechanical result of a spanning floor. When gravity pulls down on the middle of the slab, the material is forced to bow. That bending action causes the bottom edge of the concrete to stretch, creating the tensile stress that leads straight to structural failure. For decades, the standard workaround was keeping spans short and relying on a dense grid of supporting columns. But modern architecture demands sweeping, uninterrupted commercial spaces, and that traditional approach cannot meet those requirements. To build these structures, engineers must find a way to make concrete resist tension, even though the material is physically incapable of stretching. The solution is post-tensioning. Instead of waiting for the building's weight to create tension, engineers introduce a permanent artificial compressive force into the concrete before any architectural loads arrive. The system relies on bundles of high-strength steel strands, usually 12.7 or 15.2 millimeters in diameter. Each strand is sheathed in a plastic casing and coated in grease, ensuring it remains completely unbonded and free to move inside the surrounding concrete. In this transparent cross-section, tendons follow a specific parabolic curve, draped high over supporting columns, dipping down at mid-span. This achieves load balancing. When pulled tight from the edges, they push upward from the low points, directly counteracting the downward pull of gravity. All of this geometry sits dormant while the liquid concrete is poured. The process cannot continue until the concrete cures and reaches a compressive strength threshold, usually 25 to 28 megapascals. A megapascal is a metric measurement of pressure, confirming the concrete is physically hard enough to withstand high force. Once the concrete hits that target strength, the stressing operation begins at the slab edge. A specialized hydraulic jack attaches to the protruding tail of each steel tendon and applies a pulling force of over 150 kilonewtons. A kilonewton is a standard unit of force, and 150 of them is roughly equivalent to suspending 15 metric tons. Under this load, the steel strand physically stretches. Site engineers measure this elongation and compare it against calculated theoretical tolerances to ensure there are no hidden anomalies, like a blocked duct or a snagged cable. This diagram shows the hardware capturing that 150 kilonewton load. Hardened steel wedges surround the strand inside a bearing plate. When the jack releases, the stretched strand pulls those wedges deep into the plate. The teeth bite into the steel, permanently locking the force inside. That single mechanical action turns a passive floor slab into an active structural element, carrying a permanent internal counterforce that acts as a coiled spring against gravity. This creates specific architectural advantages. A conventional reinforced concrete slab spanning 8 meters typically requires a thickness of 300 millimeters. By using post-tensioning, engineers can achieve spans of 10 to 12 meters within a slender 200 millimeter profile. Trimming 100 millimeters of concrete from every floor reduces the dead weight of the building. With less mass to support, the structure requires thinner columns, fewer shear walls, and shallower foundation piles. Because the floor is held in a state of constant active compression, the tensile stresses that normally cause microscopic cracking are suppressed. Keeping those cracks closed shields the internal steel from moisture and chloride corrosion, extending the durability of the structure by decades. However, the high forces involved mean there is no room for sequence errors or sloppy site placement. This heat map illustrates the risk inside the anchorage zone. When a concentrated point load enters the edge and spreads out, it generates splitting tension perpendicular to the main force. Engineers disperse this energy using a dense cage of bursting reinforcement. If a contractor omits that bursting reinforcement, or if they attempt to stress the cables before the concrete reaches its 25 megapascal threshold, the concentrated force of the jack will split the edge of the building open. The cables are hidden and the force is silent, but this calculated tension is what permits the thin floor plates and open spans that define the modern city.